Desai sir, we may start. Others would join meanwhile.
Okay, ma'am.
Shall we start, Anju ma'am?
Yes, ma'am.
Okay.
Good evening, one and all. I am Sandeep Desai, ATAL FDP committee member, present before you. Today's session of day 6 in week 1 of the ATAL FDP RSAML 2023, organized by Department of Electronics and Telecommunication Engineering, YCCE Nagpur. This session would enrich you with the zeal of experiences from well-known academicians and professionals from remote sensing field. Today we have with us a learned expert from the area of remote sensing, Mrs. Anju Bajpai ma'am, from Regional Remote Sensing Center, Central ISRO, Nagpur, as our speaker. Srimati Anju Bajpai is working as scientist at Regional Remote Sensing Center, Central, a regional unit of National Remote Sensing Center, ISRO. Srimati Bajpai has a MTech in software systems from BITS Pilani. She has 17 years of experience in ISRO in the area of application software development in remote sensing and GIS. She has worked in the areas such as development of mobile applications, development of web GIS portals, automation of satellite image processing and feature extraction, AI, ML, DL based feature extraction from satellite data, and IoT based smart air pollution monitoring. She has contributed in the development of several softwares, including the recently developed software on transmission infrastructure web GIS portal for different states in India. Now I request Mrs. Anju Bajpai ma'am to proceed for the session and light up all the listeners with your expertise. Please, ma'am.
Thank you, sir.
You may share, ma'am, now.
Oh, yeah. My screen is visible?
Yes, ma'am.
Okay. Good evening, everyone. Myself, Anju Bajpai. Thank you, sir, for giving me the opportunity to share some of my knowledge and experience within the past few some years that I have gained in this particular area. Mainly, our focus is on remote sensing and GIS. Since our region, we are working in the Regional Remote Sensing Center, Central Nagpur, which is a regional center of NRSC, that is National Remote Sensing Center of ISRO. So basically today my topic will be on deep learning and machine learning techniques for feature extraction from satellite images, and I'll also show you a special case of electrical substation extraction that we have done here. So as you all may be already aware, what is artificial intelligence? It's the ability of a computer or a robot to do tasks that are usually done by intelligent human beings. So it's a branch of computer science under which various other branches are there. Like within the artificial intelligence comes machine learning, expert systems, natural language processing, speech recognition, robotics, computer vision, etc., etc. So then what is machine learning? Machine learning is actually a study of algorithms that learn from examples and experience instead of relying on the rules and making predictions on the new data. So it's again a subset of the artificial intelligence where we are learning from the data. That's why the name is machine learning here. So then what is deep learning then? So deep learning is a subfield of the machine learning focusing on the learning data representations as successive layers of increasingly meaningful representation. So here basically what happens is in deep learning, you have higher number of hidden layers. So that I'll be showing also. So by definition and by understanding the various branches and its subset, you can see that artificial intelligence is the first branch which has came into existence in around 1950s and around 1950s to 1980s, where then came the machine learning, where people started using the same artificial intelligence and going deep into training the machines to learn by their own data that they have collected over the period of years. And then came the deep learning. So deep learning is basically for the data which is enormous in size sometimes, and which is very difficult to interpret even through the machine learning. So all these branches have advanced because of the requirements of the increasing data size, increasing number of features that are seen, increasing resolutions and everything. So that way these branches have helped us, these technologies have helped us a lot to do a lot of researches and do a lot of good work in remote sensing and GIS also. So again, machine learning, if we see, it can be divided majorly into three types. One is the supervised learning, then is the reinforcement learning, and third one is the unsupervised learning. So supervised learning by definition is a type of machine learning in which machine learns from known data sets. So we give training examples in which already we know that this is the field data, or this is the ground truth of the particular satellite data, and then we feed that to the system or the machine, and then the data from the input data which is supervised, again the model learns from the supervised labels. So it knows that what was the actual ground truth, and from that it learns. So that is the supervised learning. Then second is the other one is obviously the unsupervised learning, in which the machine learns without any supervision. So initially you don't give any ground truthing, you don't give any label data for training. Training may you don't give any labels, just by clustering kind of thing, it will divide the entire feature space into various clusters and try to make a learning model, machine learning or deep learning model. Third one is a reinforcement learning, in which there is an AI agent basically. So an AI agent is trained by giving some commands. Okay, and on each action that it will do, the agent will get a reward or a feedback. Okay, using these feedbacks, agent will improve its performance. So it's a different kind of programming paradigm. It started with functional programming way back, and then it has come up to the reinforcement learning. So at every step, like a robot, when he when he has no idea in which room he is, and he has to clean the entire the entire room. So at every step, whatever he takes in one direction, he will get some rewards, or he has to pick a ball, say. So a robot has to pick a ball. So at every square of some size, so on every step or on every pixel square that he is stepping next, he will get a plus or minus reward. Based on that, again it will learn from all the various steps it has taken in various directions, and that way a model is derived in the reinforcement learning. So if we see main types of machine learning, may some examples just I wanted to show, like we are giving a say cat image, and we are also telling that it is a cat. So the model will also describe that what is a cat and what is a dog. Similarly, if we talk about the unsupervised learning, there we have these kind of clusters, which we will divide into three different types. Since in the feature space, these are forming three different clusters, so we will form three different classes altogether in the unsupervised learning. We don't know what it is. So finally, after seeing and after doing the further ground truthing, they are further labeled. So that is unsupervised. The third one is the reinforcement learning, like here you are seeing. So it is used for understanding that where can be some where it can hit. So like in a game, you understand that 10 times it has hit when it has gone up to this height at this particular XY. So it will learn from the model, and it will from that it will learn, and it will derive a model out of it. So why we need machine learning today? So if we talk about way back 1956, when wax machines and very big systems were there was very less space. So data storage was a very big problem, and hardwares were very big, and but the storage was very small. Then in 1980, there were these 10 megabyte hard disks. Okay, and that also cost was also very high. Whereas now, if we talk about 22, 23, we have a very small size. In your mobile itself, you have this is only very, I mean, less cost I'm showing, but you have 8 GB, 16 GB, or whatever, 64 GB also. So that way the cost has reduced, the sizes have reduced, but the storage size has increased a lot. So that's why people are storing a huge data sets everywhere, whether it's the mobile or it's the computer, it's a PC or it's a laptop or it's a tab. So everywhere there's a lot of data. So that's why now the data has, how it has to be used, that's the question. So that's why these things, these kind of technologies are now requirements of the today's time. So understanding the human brain analogy of this machine learning, if we talk about the human brain as per se, then it has dendrites. You can see these are the dendrites which are connected to the neuron, which are connected through the axon to the synapses. So the same thing here actually happens here. The input values whatever we give to the neural network. So everything in the machine learning and deep learning, when we are going further, it is mainly generally made up of a neural network. So whether it is artificial neural network, it's a convolutional neural network, it's a deep convolutional neural network or whatever, but everywhere it's a neural network. So the dendrites here, and the analogy what I'm talking about is the dendrites here are nothing but the input values. So it is in dendrites are interacting with the outer world. Okay, so the outer world inputs are taken by the dendrites. So here also inputs are taken from the outer, this thing, and then some weights are given for each data that is received. And then in the second step in the neuron, what you do is the activation. So activation is the main, you can say the neuron is the brain, as you all know. Okay, so the neuron is the brain of the entire our human brain. So there what happens is, using the weights of the received data, giving weights to received data, it will activate a particular recognition. Means it will say that it will create a model and say that this is this particular object. So that decision is taken in the neuron. So that's the activation function. And the third step is the output value, means what it is, it will try to discern what is the output. So these are some of the images. These are just like a, brain twisters, how a human brain perceives. So how we perceive. So first we have to understand how our brain works. If we want to replicate our brain, first we have to understand how our brain works. So that's the important thing. So that's how people have made all these algorithms. Of first learning from our own biology, that how we do it. So like here in this photo you are seeing, you can sometimes you feel that it is a side looking photo, sometimes you feel it is a front looking photo. Why it is? Because you have certain features in your brain, embedded in your brain, which says that if the nose is protruding like this in the sides, it means it's a side looking photograph. But the brain also says if the eyes are looking like this, then it is a front photo. Okay, so that's how our brain will get perplexed here, confused here, and we will not be able to understand that what kind of means what angle it has been taken, this image has been taken. So that's how our brain takes the decision. Second, this image also you can see that if we see it from this side, it looks like a rabbit. If we see from this side, it looks like a duck. So here also we are seeing some of the features, like this may be the ears of the rabbit, this may be the eye, this may be the mouth. So there are certain features which tells you that okay, this if these features are there, if it's a set of these features, it may be this object. This is how we are learning from while we see from our childhood and we grow up till now. So we learn by seeing various things in the real world, and we try to make these decisions. So then second is here also your it's jumping slightly, this eyes are jumping, you feel that there is one photo, eyes are here or there. That's because it's merged that way. Here also you have a old lady which is looking down, or a young lady who is looking in the back. So all these perceptions are actually done by the brain, and all these decisions are also taken by the brain with the help of features. So here also we have to define certain here in artificial neural network, how it is designed is it also tries to define various features and try to pick various features from the imagery or whatever input data you are giving. So in this case, as we are talking about the remote sensing or the satellite data we are talking about, so the input values are nothing but the satellite images, right? So the satellite images has like many bands. It has multispectral, it can be panchromatic, it can be hyperspectral, it can be microwave or synthetic aperture radar data. So anything can be a input value here. So it's an image, or you can in general you can understand that it's an image. Image is an input. So an array will be made from all the values which are there in an image, and then it is fed to the hidden layers. So hidden layers, what will they will do? They will try to pick up some kind of features which are there in each part of the image. And using those features, what it will do is it will try to understand that, okay, in this part of the image, maybe this object is there. In this part of the image, this object is there. And by concluding all that through the hidden layers and the activation function, in the output, it will try to label the things and recognize the things. Recognize the inputs. So then what is deep learning? So in deep learning, the difference between the machine learning and deep learning, so and artificial neural network, it's very small. So earlier people used to work in the ANN, right? I think some of you also might have dealt with some of the artificial neural networks. So where we used to give various inputs, and then we used to give some decision rules, right? And then it will derive an output of the classified imagery, that if these decisions are true, it's this class. If the other set are true, it is this class. So like that is a simple artificial neural network. But with the increasing size of the data, increasing bands, increasing spatial resolution, increasing number of the objects which are found in the satellite data, if you see the classification earlier and the level of classification now, it's very difficult to discern each and every object. So now the time has come, dynamically you tell that if I'm searching for this particular object, where all it is. So those kind of problems, when you want to solve, you cannot statically define the features and statically define the decision. So there comes the deep neural network, which is totally automated, and which will define various. It will actually function like our brain only, where it will individually take all values. It will try to connect to all other values, and then finally it will make it into a fully connected layer through which the activation will take place, and the output classification and recognition will take place. So it's having a lot of huge number of hidden layers in between, and between the input and the output there are a huge number of layers which are there, which was not there earlier in the artificial neural network or the machine learning based neural networks. So next important thing in this is the activation function. So the activation function, if we talk about, as I told already, it's the neuron of the of any deep learning or a machine learning model. Why it's the neuron? Because it takes the decision, yes or no, whether it's a cat or a dog, whether it's a substation or not, whether it's a urban area or a forest area. So this kind of decision is taken by the activation function. So this was first invented in 1958 by Frank Rosenblatt. So there are various types of activation functions if we talk about. One is the threshold function, which is just a step function. If it's one, if for a particular threshold, and zero for another threshold. Then sigmoid function, like you can see, for greater than zero, it is defined by a function of 1 by 1 plus e to the power minus x. Then a rectifier function where it is zero all the time, and then a linear function. Okay. And always you can define the function as max of x or zero. Then there is a hyperbolic tangent or tan h, which is also defined by a formula and given by the tan h curve. So all these activation functions are given in various layers, and finally you can see in the hidden layers, like a rectifier you can give, and in the final layer you can give a sigmoid. So that way you can define various activations, and then you can derive some results. So in any neural network, there are basically there are two things which are happening. There are two types of data flows. If we talk about the data flow of the entire network, there are two things. First thing is the feed forward. Another one is the back propagation. So in feed forward, what happens? Um Anybody? Yeah, I think we should interact also little bit. Anybody had a question till now, or anything that you want to ask or discuss here till here?
Ma'am, feed forward means the output of first layer neuron is given to the next layer as an input.
Yes, yes, correct, correct. So yeah, that's very true. So here, what we are doing is input values we are feeding to the neural network, and then whatever final decision is taken, okay, outputs are getting generated, and those outputs are actually compared with the actual value. So we keep some some test data or validation data. So whenever we train any neural network, we have three sets of data basically. So one is the training data, another one is the validation, and third one is the test data. So first we train the model using the input data and the labels. We train the model. Then second one is the validation. So validation, we what we'll do is, with the model that it has made already, with the training data inputs and labels that we have given, what it will try to do is it will try to arrive at a decision for some unknown feature where we have not given any training. So it will try to find out what that feature is. Once it gets a result, say some output value, say it's an X class or a urban class or a forest class. So it will then compare it with the validation data. So validation data may you will have other data, some data which is not given in the training but kept for validation. So then it will compare whether it has how many have gone to the correct classes, how many pixels have not gone to the correct classes. So you find out a kind of a statistics for that. Or much good the prediction is, whether it's matching the actual value or not matching the actual value. So in the entire feed forward, we do this much. Then in the back propagation, what we do is, once we compare the actual value to the output prediction which the model has done, again that goes back into the model, okay, as a feed to the model, and then the weights are adjusted. So if it is not matching, the weights are again adjusted to optimize this, means to reduce it further. So this difference should not be much. So for that, reducing the cost, the loss of this particular model, to reduce it further to zero or towards zero, what it will do is it will try to reassign the weights. Okay, and while reassigning the weights, again it will reassign the value of W1, W2, W3, and so on. And again, with the same input value, the same model will be again trained and learned, and again one model will come and one output will be taken, and again it will be compared. So this will be iteratively done till the time we define that, okay, this is the threshold till this time. If it reaches, or these are the number of iterations you can go for, or you can also tell that this is the difference or cost it should have, then you stop it. So either of the two you can select, and then you stop that learning. So the model has trained as per your your requirement, okay, accuracy requirements. So that way, these are the two parts. So then, and there is this one more important thing is this gradient descent. So in gradient descent, what happens is, earlier this is actually one important thing in this cost function, that what happens is the solution is somewhere, see here, okay, but we think the solution is somewhere here. So what we'll do, if we have, how we actually descend, so you will ask that how you are reassigning this weight. So how we do it is through this gradient descent. In gradient descent, suppose we consider that this is the kind of data sets that we are having, actual solution is in the red point, and we are arrived in the first iteration at this point. If this is not correct and this is having this much difference from the original one, so what it will do, it will change its direction. It will say, okay, you were at left, you go to the right. So it will come here. Then here also, if there is difference, it will go, okay, you are at the right, you go to the left. And again it will say, okay, you are here, you go here. So like that, quickly it will try to converge. So it's a very, very beautiful model. Gradient descent is a very beautiful technique through which we can quickly converge to the solution. So what is the convolutional neural network? So first of all, we need to understand that in image processing, what is convolution? So convolution, if you see this is a example of an image. Okay. So this image is having zeros and ones. For simplification, we have given only 0 and 1 value here. And this is a feature detector. Feature detector means any kernel of size, say 3 by 3 here it is given, or with values again here also given 0 and 1. So what it will do a direct product, means it will put this entire kernel on top of the image, okay, like this, and then like this. So it will keep it moving kernel will be there. So first it will go to one frame, then it will move to another, then next one. So it will keep on continuously moving from the first row, first column to the end of the image. This is the last one. So that way, then what it will do is it will multiply 0 by 0 and the overlapping ones, 0 and 0. So, and also it will sum. So 0 into 0 plus 0 into 0 plus 0, 0 into 1 plus 1 into 0 plus 1 into 0 and plus 0. So all will be 0. So final result is 0. So after doing this convolution, this is the kind of map that you get. Okay. So here you can see from 0, 1, 0, 1, whatever was there, you are able to get some higher values in some area and some zero values in some other. So it will try to detect a particular feature, okay, which is there maybe at this point somewhere. Okay. So that way it will try to capture some of the features and try to suppress the others which are in zeros. So that's the use of the feature detector or any kernel or the convolution, and the entire process is called a convolution. In convolution, you can also see the entire image size has been reduced to a slightly smaller one, means the outer, you can say outer boundary is removed. So always this outer boundary gets removed. In all the layers, this convolution is happening. When we are talking about deep learning or deep convolutional neural network, in every hidden layer, there are feature detectors and they keep on convolving. And last you get only one feature, that's a fully connected layer, where after which you do the activation. So this is how the convolution works, and this is how the convolution is used also for detecting various features. The next is the max pooling. So in max pooling, what you do is you try to again see that which is the maximum. So suppose here in we take a max pool of 2 by 2. You see what is the maximum value in 2 by 2? So it's 1. So it will put 1. Next, what is there? It's 1. Next, what is there? It's 0. So like that, it will keep on moving and it will try to put a max pool feature map. So again, where 4 is there, it will give 4. Similarly, where 2 is there, it will try to give the maximum value. So it will maximum values means what actually? Why it is used? Can anybody tell? Since we are talking that this is a feature, it's a feature detector. So why we are trying to capture the maximum values in the resampled data and not the minimum values? Because maximum value only represents that yes, it's a recognized feature, right? And while the zero values are not significant, why? Because they are not representing any features of the type that we are searching for. Maybe it may be some other feature, but not that what we are searching for. So that way, the max pooling tries to put all those things which are important or which are more significant in the final feature map and remove all the insignificant values from the final outputs or the intermediate outputs. So this is a particular, you can say, this is a very peculiar convolutional neural network picture where you can see this is an input image. any remote sensing or any band, or it can be multiple bands also. 3 bands also can be given as input image. Okay. So here I am showing only one image, but you can have a multiple bands here. Then next step is convolutional layer. So convolutional layer will be the next step. So it will try to detect some features and convolve it.
Ma'am, I have one question over here.
Yeah.
In max pooling or pooling layer, we generally define the shading also, right?
Hmm.
So the value of the shading should be low or high. But if it is high, then will it be any information loss there?
Yeah. So you have to define the strides based on the size of
Okay.
the feature. So if your feature size is very small, you have to
Hmm.
keep the strides less. Means it has to be compressed as much as possible. And if the feature is big
Hmm.
enough, suppose it's a big lake or reservoir,
Hmm.
okay, so then you can jump slightly.
Okay. Thanks.
Yeah. So that way you can define it. So here convolution is there. Then convolution is always it is followed by a pooling or max pooling or whatever type of pooling you give. And then finally you go for flattening. Flattening means you convert all these values into single digits. So that's how then finally you do the activation here. So if we talk mainly in terms of the machine learning fundamentals, if we talk, we should know what are the data. So data can be colored channels of various heights and widths. So many samples can be taken as input, or a single image can be taken as input. Generally, we take many images actually. The truth is, in the data we have multiple images and the multiple masks. Okay, masks means it tells you that in this particular areas there is this particular class, say reservoir is there or water is there, or here forest is there. That kind of classification vectors or mask images we give as input. And then there are validation and training data and test data splitting. So there are various data, the data sets can be divided into training, validation and test by various ratios. So like it can be 60 by 40, 80 by 20. You can trial and you can try with some methods or some ratios, and you can test whether it's able to converge or not. If it's not able to converge, sometimes you may have to enhance the training data set, or sometimes you have to increase the, you have to first understand what kind of problems are there that are done through accuracy assessments, how the accurate your results are. So then you see that whether more false positives are there, more false negatives are there. So what kind of problems are more, something is omitted more, or something is commission errors are more. You try to understand the entire accuracy structure and then try to again split the data. So you get again what you get there is a increased or enhanced model with higher accuracies. You will try means always you will try to make the model in such a way you get higher accuracies. So since all these images are in n by n size, so they are also defined by tensors, which are generalization of matrices to n dimensions: 1D, 2D, 3D, 4D, 5D, or ND. In NumPy, you have ND array. Actually, generally, all these things are done in the Python. So basically, this is one sample code that it is showing. And then you also give it in small mini batches. So small sets of input data at a time. Why? Because maybe the processing power is limited. So you will give it in batches and try to first see, converge and see in a smaller time that what is the kind of output with this input, whether we want to change something. So that way you try to model it. Next thing is model learning training. Like generally the input data will be like this. Like this is one class, this is another class, and it is not at all demarcated properly. So the any learning or machine learning, what it will do, it will try to make a proper boundary of the orange and the blue features by giving various parameters and hyperparameters to the model. Okay, and finally the inference should be following this order. It should not go like blue should not come here and most of the yellow should not go there. So that kind of inferences if you are getting, that means your model is correct. So, but with some accuracy and some plus minus accuracies, it may be correct. So that is how it is done, and it is understood. Then optimizations, there are also various optimization methods which are available, like finite step, iterative, heuristic optimizations you can give. So you can have a mathematical optimization, like selection of a best element with regard to some criteria from some set of available alternatives. That's the, so like learning as an optimization, like cost function. What is a cost function? Is nothing but your uh, how much from the actual value, how much it is deteriorating, means your output predictions, whatever is coming from the neural network or machine learning, predictions are coming or outputs are coming, how much it is similar to your actual values, that you try to see in the cost function. And if that loss is much or higher, then you have to optimize it again. So that and second part is the regularization. So regularization, may we see that okay, maybe it is fitting in one particular set of images, but in some other set of images it may not be fitting. So those things also you need to check. So this is one 3D model of the optimization gradient descent method, that basically in various you can see there are dips actually. So like this, there must be a class here. So you have to converge. So you will start from somewhere here and try to descent and go till here to make the cluster center. So that's how gradient descent will do it, and make the cluster centers faster. So gradient descent again, it is showing this is a formula of that, and actually there was an animation. So how it proceeds from, suppose it starts from this point, how it proceeds, and all it shows actually. So over and underfitting, generalization and regularization. So models with lot of parameters can easily overfit to this training data. So overfitting means it is trying to overfit to the training data itself. If you give some other data in the evaluation, it will not find out the correct features. So that should never happen. Like this image, this you are seeing the green line, it is overfitting actually. This much it should not fit to the training data. It should give a probable line here and end it there. So if it is further, it is the iterations are given, and further if it is learned, it will do this kind of thing. So for training data, it will be good, but suppose some new feature is coming, it will go into the wrong class. So that's the overfitting. And underfitting is that if it is this line and it is going inside only, so that's underfitting. So those kind of things only. So optimization also, you have to put an end to it. So that's also an important decision in deep learning modeling or machine learning modeling, that where you end it. So those things are seen through the learning rate and the loss curves. So those things are studied to understand when the learning has stopped. It has become constant for a number of iterations. Then you should stop it. Either it is not learning because your input is not correct. Okay, if your learning is not giving very good accuracies, then you can again remodel it. But if it has reached a good accuracy level and then still you are going for more number of iterations, then you have to stop it. So you define the iterations very precisely to arrive at a good model. That's the one of the challenging part of this deep learning, because inside we don't know what is happening. So it's just like a black box sometimes. When it is doing lot of iterations and it is trying to optimize it with cost functions, whatever we are giving, sometimes we miss the bus, like how it is happening. So we have to understand through these kind of graphs, like learning curves or loss rate curves, etc. So the generalization is the quality of ML model is measured on new unseen samples. So you will understand that unseen samples may how it is working, and regularization is any method to prevent the overfitting. So again, it should not be too much overfitted to the training data. So you can also add more data. So one advice is given that add more data, but how much more data? You cannot have infinite data added. Now, if you add infinite number of data sets, then you have a limited processing power. Even with, if the data sets are huge, you don't have that much huge processing capabilities still. Okay, if you want to go for very high end deep learning, sometimes you need another GPU. Okay, when we are using the workstations also with GPU also, it will take 1 or 2 days sometimes to train it. So otherwise you need to go to some cloud services and then train it, but it's difficult, slightly difficult. It takes a lot of time and processing power of the computer to do these many computations. Right, since you can understand, like image is n cross n, and in every layer we are trying to convolve it to n minus 1 into n minus 1 until we are going till 1 cross 1. So how many layers will be there, how many number of computations will be there, that's a huge computation, and that's only for one time. That's for one iteration, you can say, and that iteration will keep on going till your loss function is converged. So that way, it's a highly computing intensive or processing intensive way of doing it. So, if we try to understand the entire anatomy of the deep neural network, we give inputs, and it starts with some weights, and then again it is transformed through convolution to another layer, which is a hidden layer. Again, some weights are given, and then there are, and the output, when it is a fully connected layer, there are predictions, and these predictions of the inputs are compared with the true targets to understand what is the loss function. And with that loss function, we get a loss score, which is given to the optimizer. Optimizer again updates the weights which are given back to the layer. And again, this proceeds. Okay. So layers, the layers are nothing but, as we understood, they are data processing modules. You can have many layers. You can have densely connected network. You can have a convolutional network, recurrent, pooling, flattening, all these things. And layers, what is happening, you are all understanding. And input data and targets also, you understood that input is nothing but your image here, and target is nothing but the classification on that image. So here, if this image is given, like for example, you understand in the output that whether it's a cat or a dog. uh, the loss function is like various types of loss functions are there, like mean squared error, binary cross entropy, categorical cross entropy, and so on. So these are basically for various types of problems that you have. Like mean square error is more suitable for some regression kind of thing, when you want to fit linearly with two variables linearly. Binary cross entropy is for two class classification. When you have binary classes, means two classes, and then you want to know one out of the two in which class it should go, whether it should go in this class more weightage or this class more weightage. There, binary cross entropy. Categorical, again multi-class classification. So like that, there are various loss functions which are designed for various types of problems. So you select a loss function based on your own problem. So that way, the entire the anatomy, you have to model, architect it, or you have to model it, or you have to design it first, and then you implement and execute. Yeah, this was a this was a, I mean, animation I was talking about. So optimizer, it will update the weights based on the loss functions. So learning rate plus scheduling. So there are various types of momentum, or this gradient descent, and various types of methods are there, which will, if the solution was here in the earlier instance, it will try to bring it to the central this thing, I mean the correct one. So this will be the total trajectory, as you can say. So stochastic gradient descent, descent, momentum, variance, RMS prop is usually. So these are the various types of choices for the optimizers also. So these are now talking about some of the applications of deep learning in remote sensing. So they are used first of all in the classifications, like whether it's an agriculture field, it's an aeroplane, it's a baseball diamond, or a baseball ground, it's a forest, it's a freeway, or it's a golf course. So this was the first attempt in earlier where people, what they have done is they have given single chips of images where the entire image will correspond to one class. So that was the first attempt in the remote sensing. Then second one was the semantic segmentation. In semantic segmentation, you have multiple classes in the same image. So segmentation will assign a class label to each pixel in an image. So you can see here there are the roads here and here, and these are also the roads, and these are the urban settlements are there. These are some fallow lands are there. So like that, and some water bodies. So like that, it will give classes or labels to each object or each segmented object that it has found, and it will do the semantic segmentation. The next important application is the object detection. Suppose there are aircrafts or there are ships are there. So how to identify it? So object detection is a task of placing a box. So it will do a kind of bounding box kind of, it will draw around the bounds of an object, and it can be used for detecting vehicles, aircraft, ships, etc., and mainly useful for like applications like defense and all, where you want to know that how things are, you want to track the things basically. The other thing is application, very good application is the regression. So logistic regression or any kind of regression, you do it. Why you do it is to model certain physical parameters with some other parameters of which are geographical in nature or which are geospatial in nature. You will try to make a correlation between various types of things and themes, and try to make a physical interpretation through all those different physical various themes or thematic data sets. So regression is a prediction of a continuous variable. For example, here it is given the land surface temperature from an image. In this example, what has been done is there was a multiple linear regression which is done, okay, to create a model, um, to create a model for thermal and mixing of surface temperature data. So where various types of indices and land covers are used, and they are further correlated with the each parcel has these indices, and each parcel also has this land surface temperature. So land surface temperature is predicted with the help of the other parameters. So that kind of prediction models also you can make from other data which are you're acquiring through the satellite. Next is the cloud detection. So always when we talk about remote sensing data, the most important problems are in the optical remote sensing data are the clouds. So now earlier there were some manual methods through which you used to generate mask, and then you do certain kind of thresholding or increase the brightness and do certain things, and then you try to remove the clouds. Okay, so but now with machine learning, it's very simple. You give it this training to the data, and it will find out where all masks are there, where all clouds are there, and it will also do a painting there or a masking there. So a cloud in painting will be there to fill the obscured area. The
Ma'am,
next thing,
in this
yeah,
previous slide for cloud detection, the shadows of clouds are also there.
yeah,
So naturally, their intensity values would be different.
yes.
So how we could remove that so that we will see the clear picture? So what are the
Actually,
methods to remove those things?
totally, it cannot be removed, ma'am, but we have to increase its brightness. Basically, what shadow cloud, anyway, we will not get any data
Hmm.
within that. But in the shadow, what happens is the data is there, but slightly because of this light which is obstructed by the cloud, it is not able to give that proper signature or
Yeah.
reflectance in the
Yes.
sensor. So what we can do is we can find out that what is the dark object, or you can find out in the water body what is the dark object or zero radiance for the detection,
For
and
example,
then
yeah, in this picture,
you
generally the vegetation is there, but this shadow, dark black shadow
yes,
is there.
yes, yes.
So how it could be removed? Because in
So
the
you have
output,
to increase that the DN values of those areas.
okay.
Manually. Earlier, what people used to do is try to understand what is the threshold. Means
Hmm.
shadow has contributed to how much decrease in the radiance
Hmm.
which is received as a center. sensor. So that sensor radiance loss is added to those features, and then you try to get the radiance of those features which are in the background. It gives some result, but maybe they're not very accurate. Some
Okay.
data loss is always there when they are dealing with the clouds or the
Okay.
shadows.
Even if we are dealing with deep learning.
Yes, yes, yes.
Okay.
Only thing is we can at least obscure those things so that it doesn't comes into picture in the final models of our deep learning, and it doesn't makes the model affect the model accuracies.
Hmm. And if we are talking about the glaciers again, because the again color glacier and cloud, it
Yeah,
would mix.
yeah. Hey,
So what
cloud
about the
and
signatures? Huh?
cloud has a special this thing that first of all it is very different, ma'am. It has
Hmm.
first of all clouds have shadows.
Hmm.
Second thing is glaciers are mixed with the the sands and other things
Hmm. Hmm.
which
Hmm.
comes along with it, so it has a
Hmm.
different signature.
Only color would be the same. White. We
Yeah,
can say
color will
that
be
is
white. Color will be white.
okay. Fine.
Next is this change detection. So suppose we are having an image in the flood, etc. These kind of methods are used. That earlier what people used to do is they will see the pre-images, post-images, and they will in the pre-image they will see that what is the water extent, and the post-flood image also they will try to find out that what is the water inundation, what is the extent of water. They will take a difference of both the water extents. So these are done in the vector formats generally. Earlier, there's a manual method. I'm just telling you a simple method. So pre-flood, this was the water extent in that area, say Kerala. This was the condition, and now post this flood event, due to inundation of water in various areas, the extent has increased. Now you minus it, you subtract both the things, and you get the inundated areas highlighted as red here. So those areas basically there is no water body actually there, but due to flood it has been inundated by the flood water. So those kind of things earlier it was manually done, or with some image processing also. Then microwave and so many other things, R data was used and all, which is definitely it's a very good data when we are talking about floods, because in the floods you have lots of clouds. So in the SAR data, it's all season data. It can penetrate the clouds, and it gives the backscattering. So that way, it gives very nice results nowadays with the SAR data. But still, with machine learning or deep learning, again, if you train, you can totally make this process automatic. So whatever you were doing manually, some processings you are doing, that if you train with all those past flood data, if you train a machine learning deep learning model, you can do a lot of change detections quickly through the deep learning model. So these are some of the good topics. And then another one is the super resolution. So super resolution is a method in which suppose you have this is also a high resolution image. Say it's a 1 meter resolution. You understand, are all of you aware of the spatial resolution, ma'am?
Yes.
Yes,
Few
no?
lectures back, the introduction has been given.
Okay, ma'am. So basically, a spatial resolution is nothing but in 1 pixel, how much area you are seeing on the ground. So if I say if it is a 1 meter spatial resolution, that means in 1 pixel, okay, 1 pixel, you are seeing 1 meter by 1 meter of the ground. So that is the spatial resolution. One point, like a map में scale होता है, वैसे ही the spatial resolution also talks about the satellite data details. So in 1 pixel, if you're getting 1 meter by 1 meter square of Earth area captured, it's the 1 meter spatial resolution. So suppose you have an original image of 1 meter spatial resolution, and you want to get further higher resolution without having a new sensor for it. How you can go do it? Through super resolution. So that's another very good application of deep learning, that from 1 meter to 1 meter you can go up to maybe 0.25 to point into 0.25 uh, meters spatial resolution. So you can increase the degree of details that is seen here to a very higher extent, sometimes 4 times, sometimes 3 times, based on your model. So these kind of all problems were given many a times, even in various competitions, and very good results are coming. So these are all very good applications, of the deep learning as far as remote sensing is concerned. Now, talking about some of the frameworks which are there, so you have to use lot of frameworks to develop a deep learning model. Mostly, generally, what I am using personally, if I tell, is mostly I'm using Python programming along with various libraries. So there is this PyTorch, Cafe Chainer, PyTorch, so Cafe 2, and Theano, TensorFlow, Keras. There are so many different libraries which you can use, and Microsoft also has this cognitive toolkit, etc., through which you can model, you can define, you can use it for the entire process flow. Means for the entire programming of the machine learning, you can do through the multiple, libraries, not with one library. Sometimes you have to use multiple libraries. Like when I use TensorFlow, I have to use NumPy, I have to use SciPy, I have to use this scikit-learn, I have to use Keras also sometimes. So it's not one, and Matplotlib. So many things and utilities are defined for everything. So basically, these are some of the things, and so you also need to have a good GPU, distributed GPU, kind of distributed systems. Also, you can use. You can use the Python or NumPy or R interfaces, and you can also use the CUDA, or you can also go for the open source. Okay. And then deep learning frameworks, these are different frameworks which are interrelated, means they can work with each other. Like TensorFlow can work with Keras can work with Theano, TensorFlow, and CNT. So there are so many things which can work with each other. Okay, interoperable kind of thing. So you can try it out. You can see some of these things, and some are available for GPUs only. Some are available for some are available only for CPUs, and some are available for GPUs also. So if you have GPU enabled library, it is much better. It will run faster. It will complete your iterations, maybe which was taking 1 day, it will be completed in 1 hour. So that kind of difference you can see with this. So that's all for this session. Thank you. Any questions are there?
Yes, dear participants, do you have any questions?
Madam, in regularization, do you need hyperparameter tuning?
Yeah, like weightages are tuned as per your mainly weightages are only generally tuned with the kind of losses which are happening. You try to understand why, which types of losses are there, and in which particular class it is there. So there, in that direction, you try to move the weights.
Suppose we are getting accuracy, some XYZ accuracy, then how we'll come to know that whether our model is underfitted, overfitted? How
Huh.
we'll come to conclusion?
That actually in the next session it is there, accuracy analysis. I have given that. So actually, what happens is you have to first understand that where are the, you have to understand all those four things. There are four things: true positives, false positives, true negatives, and false negatives. So there are four parts of the accuracy. One is if it is a suppose I am going for a substation class feature extraction, whether truly it is identified, recognized in a certain pixel, why for, or whether falsely it has been identified as substation but it is not a substation, whether the negatives, means the which are not substations, those areas, whether they are true negatives, means they are given zero class or no class, or whether they are given false negatives, means they were substation part and but they are given as no class. So we have to understand the entire accuracy matrix or the kappa coefficients. There are a lot of statistics through which we can understand that where our model is lacking and where we need to improve, what has to be improved, what kind of data, whether training data has to be increased or it has to be given more to the validation. Where it is lacking, you will get to know through that only.
Google also provides GPU, TPU support.
Yeah.
So for TPU also we have to go for the same procedure as GPU.
No, TPU is not supported in all the libraries. We have to see. It is generally supported by NVIDIA uh, libraries only. NVIDIA also has a set of libraries for doing deep learning. Generally, TPUs and very special kind of these hardwares generally are coded programmed to that, as far as I know till now, because there are very advancements which are going in many libraries. Till now, what I have used and seen is this much, that TPUs and some high-end, higher accelerated, other than GPUs, if you want to go for. Uh, Generally, people use NVIDIA's own this thing, or maybe TensorFlow also provides. I don't know. You have to see that. I have not never used that.
Madam, I
Thank you,
have
ma'am.
one question.
Yeah.
Uh, for classification, means how to choose the deep learning model. Means do you generally choose the readily available deep learning model, or you choose you design your own model?
Yeah, for every problem, sir, we have to see what kind of features are there in that.
Okay.
Whether those features you can easily get through convolutional neural network or deep convolution neural network, then you can go for a DCNN kind of encoder decoder kind of structure. If that problem is not related to that, if it is a change detection or some other thing, then there are some other methods through which you can do it. Other than like unit, there are methods RCNN and other things are there which you have to go for. So you have to see that for this particular problem what kind of models are available, and then you try to use. Then for like super resolution, there are spatial attention networks are there. So that gives attention to a particular, means you have to train it for that. If this kind of topography is there, then how you are going to, or this kind of image is there, how you are going to super resolve it. So all those things you have to define in the model. So there spatial attention networks are used. So there are various things which are available. For everything you have to explore what is the latest, then you have to implement it.
Okay.
Ma'am, I have one question. Like, suppose we are getting AUC value of 1. So, what we can conclude means whether can we say that our model is good?
Hmm. Maybe or may not be. I told you that it may be overfitting.
Huh, and like so, accuracy also we are getting like 0.99. So,
It
means
may be
what?
overfitting problem. It may be.
Okay,
So accuracy we are getting because validation points are not much
okay.
of the similar type. So that's why you are getting. So you have to see with by giving various types of. So what we generally do is like in our case in like remote sensing when we are doing. So different types of different season data we will give. So in one season, radiometry is different, like summer. In the winter, it is slightly different. Slightly different features are surrounding the same feature. So the deep learning, if it is not able to very clearly identify the feature itself and not the with the background and all, then it will show the actual problems. So you
So,
have to give some data which is not so similar also.
okay. So, we can add some noise over there or what we can.
Noise for simulations you can add.
Hmm.
Finally, it should work on the actual things.
Hmm. Hmm. Hmm.
For
And
simulations, you can use, ma'am, some dummy things you can use for simulations. I also do that. Like sometimes I don't have enough data in initially. So initially you can do some simulations, give it and check how it is working. But
hmm,
later on, you should validate with the actual things,
actual data.
actual data.
And log loss is suppose we are getting greater than 1, then again it is a problem, right?
It is a problem. Loss if it is more, if it is a problem.
Mm-hmm. Thank you.
Thank you.
Ma'am, one more question. On small data set, I have applied regularization. Then I have seen that accuracy was decreasing. Should I conclude that there was a overfitting problem and that's why accuracy is reducing after regularization?
Yeah. First, it will
And for
decrease, and then after giving more training data sets or after tuning it further, it will increase.
and
Initially,
for
it will
large data
decrease
set,
because You have never given any data, means any different type of data. So whenever you give any new type of data, it will first decrease. Then it will again increase because the model has shifted its minima, maximas, in the gradient descent. It has shifted. So now the things which are reflecting is coming at some other point. Again, it will try to converge. Am I clear?
Yes, ma'am.
Any other questions? So I think, ma'am, you may continue with the next part.
Okay.
Thank you. Thank you for this session.
So I shall start now then.
Yes, yes,
Okay. I'm sharing my screen again.
yes.
So this the session 2 is about this very special application that actually we have given earlier in a competition of ICETCI in 2022, where it was an international competition in which various teams have participated and submitted their results and their models. They have discussed and they have presented also, and the winning team, there are various teams and winning teams are declared and they're presented their works. So our basic problem was this electrical substation extraction from using deep learning from the satellite imagery. So first, understanding why we chose this problem is because the power infrastructure that I basically personally, if you talk about me, I have worked with this Transco, Mahatransco, TS Transco kind of transmission infrastructure utilities. So these are all the companies or organizations which are basically providing the electrical transmission networks. So basically, if we talk about the power distribution, it starts with in this generation, and then the very high voltage or extra high voltage this electricity which is generated from the generator are further transformed to a higher voltages sometimes, or it is also down converted, means transformed to a lower voltage also, and that all is taken care by the transmission grid. So there is a generation grid where you have hydroelectric plant, you have nuclear plants, you have coal plants, etc., which generates a very extra high voltage. So they have a generation network, and they are connected. These extra high voltages are connected to the transmission network directly from there itself after generation, and then that extra high voltages are converted into operating high voltages. For industries, the voltages are different. When we are giving it to factories, it is different. When we are giving it to medium-sized power plants, if we are giving to industrial factories or something users, it is higher voltage level. But that is all done in the transmission grid. Then further it comes down to a lower voltage level in the distribution grid, further transformed down, and then after that it goes to very small, like voltage levels of 3 with 3 megawatt substations and all. They are managed and given to the 50 kV kind of voltage levels are given to the household levels. That is done by the distribution. So that's what. So we have done this feature extraction of electrical substations, which are having generally having basically power transformers, okay, and some other things like buses are there, feeds are there, okay, feeders are there. So this is a particular peculiar ground photo of an electrical substation. You can see here. Okay. The basically here to avoid this charging of this, and for safety purposes, they put lot of this stones actually here. That black color, whatever you're seeing, is stones actually. So this is a peculiar, signature which we see from satellite data also. Here you can see in the satellite this black color signature, which is very peculiar. So we thought, why everywhere we have to map all these substations everywhere? So there should be some whether can through machine learning or deep learning, whether it is possible to automatically extract the extent, because it is very when you see from the satellite image, it's very clearly defined, and even inside whatever is there, that also with some higher resolution, some methods it can be, maybe that also is the next challenge, maybe that also can be slightly, some of the assets which are there in the substation also can be picked up. So that was our problem statement, that whether we can extract it automatically through deep learning or machine learning. So we have generated some 100 images of size 750 by 750 RGB 8-bit data with spatial resolution of 1 meter. So we have given it as a starting kit. So there was some 25 images test data, 25 images of evaluation data, and accuracy metrics we have kept as IOU and kappa coefficients. Then these were the input images, and with the ground truth we got this was the masks also we have given along with this data as the training masks, and with the three models we got these kind of outputs, which was I mean very good as far as this automatically extracting these features from images is concerned. So we got a lot of solutions from various people, and we saw their accuracies, as ma'am was also discussing just now, that how you decide that which one to select. So we basically have gone for the accuracy metrics, and the kind of architecture they have used, how many iterations, their learning rates also we have seen. But mainly we go with the classification. When you're talking about, we see the accuracy metric. The solution one was like they basically, the problem was they require sufficient land area and electrical safety clearance. Substations are of different capacities, they're used in for various purposes, they have various structural sizes, various voltage levels have various areas, so area or size is also not the same. And labeling of substations is not a simple process that way. So so this was the input that was given. So the first methodology has done a semantic segmentation of the satellite images with the help of deep learning framework. So the images were taken from satellite, so they have done the overall segmentation in three processes: pre-processing, semantic segmentation, deep learned semantic segmentation, and post-processing. So here the convolution also are of various types. So they in the first one they have used the address convolution, in which you don't go for the kernel size, you go for 3 by 3, but there is a dilation also that you go for. So dilation, if it is of 2, then you jump 1 here and go to the second one. If it is 3, then you 1 2 3 you leave, and then fourth one you put it. So it will convolve with all these pixels rather than the 3 pixels. So what it will do is it will quickly try to, you know, convolution will happen quickly. So there will be lesser number of these images, hidden layers will be lesser. So computations will be fast. And since the substation is slightly bigger in size, so with that also we can extract the major features which are there. So through address convolution, they have increased their computing this thing. I mean, of power of the model, means it will take lesser time to compute the same thing. So there was an encoder and decoder here with a deep convolutional neural network, and the convolution was address convolution. And then finally a sigmoid activation they have used, and then also they have in the decoder also they have concatenated by upsampling all these things. So they have used basically a modified DeepLab v3 framework. That's a framework which is available online. So it is already having a backbone, means it is already developed for certain features. So they have included the substation as a sub feature of that. So it has various classes already in the model defined. So that same architecture they have added these layers, and they have tried to model the substation also. So for the training, mask for each image has been taken, and augmentation has been done. Since we have given only 100 by 100, now what happens is sometimes with less time and with the kind of feature that you have selected, it may not be huge in numbers. So it may be 100 or 200 or something like that. You cannot give more and more. You cannot keep on increasing the training data sets. So at that time, you have to do a data augmentation. Data augmentation is what, like ma'am also has told, like you can do some rotation, scaling, translation of the images itself. So if the substation is like this, you rotate it slightly and then you give this image, then you translate it, make it small or make it big, and then you give again one more image of that. So like that, you do a lot of augmentations, and then you shift the image, you cut it. It was cut like this, it was in the center, you cut like this, it is in the sides. So like that, you do various data augmentations for training to increase the number of training data sets. Okay. And then they have divided into 80:20 ratio for training and validation, and 1 lakh epochs they have run this training, and learning rate was 0.1, decreasing 0.1 for every 2000 epochs. So these were the sample input images. You can see these are the substations actually. These are the substations. This is also. Here there is no substation. So you can understand that so that's what I'm telling now. You have to also give some training samples in which that feature is not there. There is zero result. So that you can find out that whether that image also it is trying to depict means what kind of problems are there, just to understand that. Different types of inputs you should give. So this was the learning rate. You can see that it was losses are also, these are decreasing, but after sometimes again it is increasing. So we have to stop in between somewhere. And learning rate, it is also going down. So if there is no further learning after some time, there is no further learning after some epoch. So there we can stop. If there is some learning happening, then we can keep on going, but there is very less learning rate here, so we can stop. So here then results and discussions we can see that these are for the first solution with deep lab, modified deep lab v3. These are the kind of masks which were given, and this is the kind of output. Very nicely you can see that it has demarcated the substation boundaries. Only it has these areas which are brown, and whereas there is no boundary at all here. Those are not demarcated, but that was anyway that was also understood by us also that it will be difficult. But some other features also here you can say, since other assets are there, it has demarcated that also substation. So it was a good result. Solution 2. Solution 2 was through a Detectron 2. This Facebook has made this particular architecture or particular deep learning model like Detectron 2, which is a deep learning framework of AI research team, Facebook AI research team. So it has achieved top results in data sets like COCO instance segmentation, and COCO person key point detection baselines. It uses mask RCNN architecture for instance segmentation. So mask RCNN is a different type of architecture in which what you do is first you try to find out, do the object detection. So you draw a B box for all the objects which are known to you. And then with that, those B boxes, at every B box, okay, at every B box, or a particular B box where you feel that means the model says that it is a substation, there you do a mask RCN, and there you try to find out what are the masks. So that way, what it will, why it is good is, first you are doing a recognition itself. So first it's an object recognition. So first you say whether it's a substation or some other object. If it's some other object, you need not compute anything. So that way it's very fast. This method is also very fast as compared to the other methods which are there. So then within that you do the mask RCNN. So within that, and then you try to find out what is the extent of that. So it uses the ResNext 101 FPN based feature extraction architecture for mask RCNN for carrying out transfer learning. So earlier already it is trained for some other features, but to train it for substation, you basically do the transfer learning for the ResNet 101 architecture. and you segment your images. So they have done it for 10,000 epochs, and Jupyter notebooks, paper-space they have used. Then with various types of this model names like ResNet 50, 101, 50, 101, ResNext with FPN. So they have done, they have used the weights, they have assigned the weights from scratch, or they have used the transfer learning. Okay, so transfer learning may they have used the COCO instances which are already available and transferred the substation information also added to it. So if you do a transfer learning, what they told is then your IOU is increasing, means your accuracy is increasing because more attention is given to only the objects which are of our use, and it is not means confusing the features and unnecessarily not wasting time in computing other things. So it has increased the IOU. Then third solution was through this UNet. So UNet is also a segmentation, and they have also done a custom loss, designed a custom loss function, because in their particular solution, whatever they were getting from the unit, they were having overfitting problem. Since I told you, since we have given 100 cross 100 images, because in one state substations are only hundreds in numbers, so we have given some 150 images, like the images and samples like that for this competition. So they have to overcome this overfitting. So here they have defined a custom loss function, and custom data augmentation also they have done. And then finally so in the encoder, basically they are having ResNet 50, VGG 16, VGG 11. So best results they got with ResNet 50. Okay, overfitting is here in ResNet 50 they got lesser overfitting, and then they have used the loss function of Jacquard loss and uh, Turnos net. Okay, so and they have made their own custom loss function, so which is a combination of dice loss and the Jacquard loss. So and dice and binary crop entropy, sorry, dice loss, Jacquard loss they have seen. So they have used this a combination of dice loss and binary cross entropy. Why? Because this is also a binary problem of 0 and 1, and dice loss is also a probabilistic approach to use it. So then we will, when we got all these results, we have made this competition web page in the Coda lab, where any means participant, when he uploads his data online, it will automatically find out with the reference that how much is the intersection of union. Intersection of union is intersection over union, means how much it is intersecting with the output divided by how much union is there. Means in both, if it is substation it is union, in one out of the two if it is both it is there, it is intersection. If only in one also it is there as substation, that pixel, in any of them, then it's a union. That if you take the total, it's a union. So IOU will tell you basically that what is the accuracy. So actually IOU should be 1 in ideal case. Why? Because if the extent is same as the actual one, then intersection and union both will give the same result. So dividing both of them will give you 1. So so we have done that, we have added all these means metrics in the this IOU metric in the Coda lab competition page, and automatically it runs and gives a score to each upload which is happening. And it also has it will also show a leaderboard there. So it will show that ranking of various people, and the statistics also, then in which day how much this how many uploads were there, and who is leading the leaderboard. So that way it was a very real time and interactive competition. And then further after this we had an evaluation. So this was the first for screening and first scores that we have given. Then second was further when they have submitted all their models and with the evaluation scripts, then we have evaluated their models with some external data also. And also we have calculated the kappa coefficients there, because since it's a classification problem, so we considered that solutions with IOU greater than 0.5 and kappa coefficients greater than, means higher, should have a higher chance of having a good model. So basically, as I told you here, important things are these true positive, true negative, false positive, false negative. So the probability of being it correct and probability of being incorrect, these are basically calculated using this. So these are generally, basically you might have heard about the accuracy and recall. These methods are some of the earlier, statistics which are used in the kappa also, to generate the kappa coefficient. So these were the 10, participants who presented their results. They further presented through their virtual session, and their kappa coefficients and IOU were like this. And these are various types of networks that they have used for deriving the same, solving the same problem. So another similar attempt in deep learning we have done for the automatic extraction of non-timber forest produce using deep learning and image processing techniques. Here, this is any questions till now? First of all,
No, ma'am.
okay. So can I go to the next example?
Yes.
Yes.
Yes,
Okay.
yes, you may.
Okay, because continuously I was speaking about substation. Now suddenly I will be changing. So now this is another application of automatic extraction of this non-timber forest produce using deep learning and image processing techniques. So here what we wanted to do is, what is non-timber forest produce? These are the forest produce other than timber, means other than wood, for construction and all, whatever is given is timber. Other than that, whatever forest products particular tree is giving, that's called a non-timber forest producing tree or products. So they include the fruits and nuts. So they are very much useful for the tribal welfare. Why? Because tribal people, they depend mostly on these NTFPs for their livelihood, because they provide them with vegetables, food to eat. They provide them some kind of business, small business that they do. So all the livelihoods and the wood, everything is provided by these by the trees basically. So there was a demand earlier that can we count, can we do a kind of um, tree identification, tree inventorying, and identification of the, not only identification of species but also counting how many species are there and where it is. Kind of maps can we give to them so that easily they can go, because forest is very dense. They don't know, everybody, means the tribal people who are living there, they don't know where what is, where they'll find a particular resource. So if we give them a resource map, they can easily go to that particular location and fetch a particular product. So if we talk about NTFPs, they include fruits and nuts, vegetables, fish, medicinal plants are also part of it. Anyway, resins are also given by the trees, essences, and a range of barks and fibers such as bamboos, rattans, and hort of other palms and grasses. NTFPs, whatever we have included in our study, because of the kind of training data sets that we got enough and all, we have selected some out of all the different biodiversity that we have seen. We have selected this Shoria robusta, then tendu, bamboo, teak, mango, tamarind, and mahua. And we went for the field visit. But after doing the field visit, we could only include the four different species that I'll be telling you. So our entire architecture that we have designed for this was based on the training and test and validation of the model. So how we do it? First, we have to understand how we can detect the individual tree crowns from imagery using object detection. So there are various methods: SSD, YOLO, RetinaNet, etc. Then you have to go for identifying the tree species using deep learning models like ResNet or MaskRCNN, etc. So backbone, you have ResNet with or without feature parameter network, and transfer learning also we can do with neon tree benchmark dataset. That is a national ecological observatory network. So already there are so many benchmark data sets which already have many tree species included, but they don't have your own trees, means Indian biodiversities. They may not be included, maybe developed by some other country. So you have to enhance them. Generally, if you take any existing backbones, you have to enhance with your own data, and then use the similar kind of model. So this was our earlier architecture that we have planned, that we will take the images and make it into 256 by 256 image chips, and further we'll do an encoding decoding, and further we'll try to find out which is species, tree species. So first detection of tree crowns from satellite imagery, like you can see Shoria Robusta at Bandhavgarh Pachpedi Gate. So tree recognition with tree count you can do through deep forest. There is a library through which you can find out the individual tree crowns. So after that, we have to go for the mask RCNN with or without RPN or ResNet backbone. These all were our how we decided we will go for this actually, and we started with manually tree crown delineation, and then training the data sets. So we have gone to the field for getting the training data sets for identifying every tree, giving the GPS locations, photographs, and details about that, and then feeding it to our backbone ResNet 50, and then we can do a bbox regressor or a FCN segmentation, and then finally we can find out where all the particular class of trees there. So basically, after doing an object recognition is the semantic segmentation. So detect different instances of same class. So the four selected after doing the field work, these were the four selected tree species. One was the bamboo. This is a bamboo actually. Then second one was Tectona grandis. This is a teak or Tectona grandis. Then third one was mahua. Mahua is also now some of the species are now in the very dangerous this thing. Then shisham or Hardwickia bainata. It's not shisham, sorry, it's anjan. It's Hardwickia bainata. So with the satellite data that we have it was having a 6-band data with with even near infrared, red edge, and deep blue and blue, red, green, NIR. So there are almost 6 bands which are available to us, and for each band with the field data we could find that what are the different types of signatures of each tree species that we see in the satellite image. So in satellite image it looks like this. So Anjan, you can see it is having a very, this is a false color composite, so don't get confused that why it is looking brown. These are all green trees only. But since we are using here for depiction, just I have used the red edge also.
Ma'am,
Yeah.
here what is the resolution of this image to
Yeah.
define the signature?
Yeah,
So
this is
at
a
which
0.3 meter spatial resolution, and multispectral was 2.5 meters. So I have
Okay.
done a fusion of both the things,
Okay.
panchromatic and this, and then I got this. So some trees which are bigger in size, like Hardwickia, have a bigger crowns. You can get a very good detailed, detail. But which are a very small, like mahua or teak and even bamboo also. Bamboo, sometimes it is very big, sometimes it is very small. Okay. So it has a variation, but whereas these things are coming like this. So that's why in somewhere you are seeing that pixels are not enough, and somewhere you get a good details. But still we went ahead, whatever were more in density for training, we went ahead and we used our deep learning model. So again, we have used the similar kind of architecture of DCNN with actress convolution, encoder and decoder. Um, and this one again we have used the sigmoid activation, and then we have done a prediction. So this was the result of the prediction. Like these are all the teaks, the light green whatever you're seeing, and dark ones are the, this is actually a binary this thing here. Teak is actually Hardwickia bainata is also used for agroforestry to increase the productivity of the other species which is there. So here, I don't know, maybe of that reason or what, it is a binary this thing. So either generally it is a teak or it is a Hardwickia in this area. So we got around with IOU, we got 0.81 in this. And we have used this DeepLab V3 framework, the similar one that was used in the substation. And we have augmented images which are fed into the network, and individual images are learned. And then address convolutional layers are also used here. And output received are also spatial pyramid pooling is done. So that's a different type of pooling. It's not like max pooling. So it uses the pyramids kind of pooling. And then finally, we get the binary classification with the semantic labels in the decoder section. So here you can see these are the results. Yeah, so in the IOU, we can see it was 0.806654, and the other one, yeah. And this is also for teak as well as the, this is another image. So, any questions are there, ma'am? Further to discuss?
Uh, Excuse me, madam.
Yeah.
Whenever we are going for the fusion of two types of images, in that case, the size should be same.
Size means, yeah, actually the
Image size will.
extent and which we will get the fused data will be the overlapping section only. We can fuse for the entire area, but we'll get enhancement only in the area which is intersection of both.
Okay.
So generally with the same sensor, what we get is 2.5 meter with the same width, I mean, same area of Earth, and in 1 meter also same area of Earth.
Okay.
Regardless of the width and height or number of pixels which are there, it will have the same area covered on the Earth or swath.
But the number of pixels are different, no?
Different, yes.
Okay.
So finally, it will have number of pixels of the higher resolution rather than the multispectral. Multispectral only will give you the color.
Okay.
Color and the basically here actually what how we have enhanced here. I have not shown any slide for that. Is this is deep learning is okay, but entire the training data preparation I have done through object based image analysis. So in that one, actually, what I have included is this graphical analysis of spectral characteristics. So once I got all these different, images, I have done a spectral analysis of the characteristic curves. So I have 6 bands. I have seen that what are the different types of patterns which are there.
Okay. Yes.
Yeah, and understanding those patterns, I have made certain rules that if in the objects after segmentation of the objects, if this object is having this kind of pattern, then classify it like this. So like that, I have generated already object based image classification I have done, and those objects I have given as input. So the input part giving means making the training data set also has been automatized in this particular method, because this challenge was for a very small time, so you have to do a lot of pre-processing, post-processing, everything.
Yes. Yes.
So we have done it in a totally automatic almost manner.
Okay.
Yeah.
Thank you.
And one more video actually I wanted to show you. Just I will show.
Ma'am, these
This-
signatures are being used by you as a ground truth for the final performance evaluation of the complete algorithm?
No. These are just some sample images that I have
Mask.
just kept for presentation.
Okay.
Yeah. Now here actually, if you this is an online lecture that I used to see a lot for understanding, because the deep learning is considered to be a black box, and how it works for a simple problem like character recognition, how it works. So it is explained here by I think one blue, three brown, something like that. One good lecture series are there. So that I'll just play to make you understand the deep convolution neural network. So I think this might have made it made a very clear picture. What he is discussing here actually, could you get the audio?
No, audio was not.
Okay, so then I will just replay a little bit. So he is telling that activations in the first layer, it will determine what are the activations in other layer. And finally, what is the final output? So this is very similar to neurons. So if these are fires, these set are fires, it will cause the others to get fired, and finally this will get selected. So these are 784 neurons in a line. So this has caused activation of this. 9 has caused activation of this in the next layer, which has caused activation of these things in next, and then finally 9 will be selected or 0 will be selected based on the input. Yeah, now we can discuss further on. So have it given any clear picture of what I wanted to share, because I wanted to show some animation so that it will be more clear when we see some animation. Sometimes some of the things, visually we can understand better. Yeah. Any more questions are there, ma'am?
Dear participants, is there any question from you? I think, ma'am, it is actually the presentation was very, very much clear. Starting from the what is artificial neural network to the applications. If they have some questions, they will definitely communicate. We will definitely communicate to you through mail also.
Yeah, sure. I'm writing my mail in the chat box.
Yes, yes.
If you have any further questions, you can definitely contact me. I will try to help you and collaborate with you as much as possible. And this basically opportunity, I would also like to say that we all should collaborate further in doing. We have done some experiments definitely, but you also, since you are more into academics and all, you may have better ideas, better ideations, and some problems which are required, and also people who can work for it, some students, so we can better collaborate and do certain new things. Generally here internship nowadays 6 months and above they are taking, and so we all can work together to bring some good changes with the new technologies that are there. There are a lot of frameworks which are available, lot of data sets and training data sets which are already there. You can use as a backbone.
Yeah.
So like object detection, Coco data set is there, and ImageNet is there. Okay, Facebook has separate one. There are various types of backbone data sets also available. Various architectures are already defined. Like you have seen ResNet and ResNext is there. So you can use a lot of libraries, lot of architectures which are existing.
So
Codes are also
basically,
existing.
basically the transfer learning concept we need to use
Yeah,
for our
yeah.
new database.
For new data set, and we have to first understand that which particular architecture best suits our need, which particular custom loss function, but we have to understand the architecture, and certain changes are required that we have to make.
Hmm.
That much understanding if we get, with our understanding, that much understanding, I think we can work with so many things which are available online nowadays. Each and every program is available. Even you have AI kind of means applications which will solve your problems of programming. So those kind of things are coming. So later on, programming will not be a bigger problem. Bigger problem is understanding.
Yeah.
So since AI is such a, I mean, it's such a, complex thing or complex network that is working, and everything inside is black box. So nowadays there's certain libraries which also are basically for defining what is going on inside that. So these libraries will try to discern that at this particular juncture why this decision has taken place. So those kind of things are also there. So we have to try to more understand that what is happening and what is the solution, what could be the probable solution, and then go ahead. So
Okay.
that way it will be good.
Yeah. Ma'am, when we are talking about the feature extraction in detail, can we go for YOLO Tiny? Because in the solutions which you have discussed for the substation extraction, YOLO was there. But when you are talking about the YOLO Tiny to find out the minute features of that particular object, can it be useful?
No, YOLO is basically an object detection only.
Yeah.
YOLO has to be combined with mask RCNN. So instance segmentation. That's actually it's an instance segmentation. So at that instance, when it's the substation object, it has to do the segmentation and derive the extent.
Okay.
Since our problem is not recognition basically. In satellite image mein, if you give a bounding box and you say ki yahan pe there is a substation, that's not enough for us actually.
Yeah.
We have to remove every background, we have to demarcate the entire feature, then it has some meaning.
Okay. Yes. Mushrif sir, you were supposed.
Yeah. Okay, thank you, madam, for your very informative lecture, and we'll be very happy to collaborate with you. So
Yes.
when you will be in the campus next week, we will surely discuss about it and
Yes,
what way we can collaborate.
Yes, sir. Yes, sir.
Yeah.
Sir, one more person has raised his hand, Karuna Kirwale. Yes, sir. Thank you, Yogita ji. Thank you. Thank you so much.
Karuna ma'am, you may unmute yourself and ask the question.
Yeah, thank you, ma'am, to give me opportunity. It is very grateful to have such type of sessions. It is very, very, very useful for the further research for us.
Yeah.
And thank you very much, ma'am.
Yeah, it's my pleasure, ma'am, to have a interaction with such learned people.
Thank you, ma'am. Good night.
Good night.
Dear participants, I would request you to please switch on your camera so that we can take a group photograph with the speaker. Yes, other participants, please switch on your camera for a group photo. We'll take one more. Others, please, those who have not switched on, please switch on the camera. Yes, thank you so much.
Thank you, ma'am, and thank you one and all to be part of this. And it's a good opportunity to come here and talk to some good professors which are working in various new technologies and implementing various things in their own domains maybe, and some of our domains also. So this exposure, I think I wish that should bring more and more number of collaborations, teams working together in Nagpur city. And Nagpur is progressing quite a lot, but because of this COVID in last 3 years, slightly it has slowed down. Maybe we are feeling, I don't know, academia how it is. It may be faster there, but better there. somehow they are coping with online, offline kind of modes. But here also a lot of interactions were very less and stopped in between almost. And so again, it needs to revamp. We need to fasten up and make more teams and work together. And of course, we have to build more new technology savvy groups of students, and which
Ha.
are the futures.
Yes, yes, definitely, ma'am. So, on behalf of the organizing committee member from Electronics and Telecommunication Department, Yashwantrao Chauhan College of Engineering, I would like to thank you, Anju ma'am. Your session was really a wonderful, and you have started from the basics of what is the artificial neuron is, and gradually moving towards the machine learning, deep learning concepts, and the use of the optimization and gradient descent optimization method within the 3D model, which we have seen. You also just touched upon what is the different kind of input data, target data, testing, training, and validation data, which could really clear the participants' view regarding the classification, validation, and the accuracy. And also we have seen few applications with respect to object detection, cloud detection, change detection, or the regression applications in the remote sensing. And then you have touched with the different frameworks you have used in the remote sensing applications. And then we have seen that case study with respect to the extraction of electrical subtraction from the satellite image, to the different solutions which is provided, and the finer timber, non-timber forest extraction. So really it was a very informative session, which gives us the insight that how the academician, which we are considering as a basic, can be converted into the applications. So thank you so much for your time and the very informative session.
Thank
And
you.
okay, thank you. And here also, I would like to thank our coordinators and the other members from the team RSAML 2023 from ETC YCC for making this online week successful. So thank you once again to all. And I request the participants to be present right now here even after this session, because we are having our online quiz over here, and followed by the today's attendance and feedback. And we will meet again on Monday at 10 a.m. at the YCC campus for the formal inauguration of this 2-week ATAL FDP at ETC YCC at 10 a.m. and followed by the offline 1-week program in the campus, which would include the hands-on experiences of different applications of remote sensing. So, ma'am, once again, thank you from all of us.
Thank you, ma'am. Thank you. Bye-bye. Can I disconnect?
Yes, sure.
Thank you.
Dear participant, I will first share the attendance link over here. So fill the today's attendance form first, and then you will get the link for quiz uh, in 5 minutes on your mail. So be in the classroom itself. You have to attend the online quiz based on the sessions which we have carried in this 1-week program, online program. You have to attempt the quiz, and it is mandatory for all for online evaluation. Then for the next week assignment, you will receive few files, papers, and the assignment through the mail itself, which you have to complete in the offline mode of this particular FDP. Please do not leave. You have to tell us whether you are able to attempt the quiz or not. Prior to that, please fill the feedback as well as attendance form here. Dear faculty participants, you might have received the quiz link in your mailbox. Please let us know in this message box whether you are able to see the quiz link or not. Comment on the chat box as Y if it is visible to you and you can attempt it. Please reply in the chat box.
Madam, again showing error.
Through the link which you received for quiz?
Yes, madam. Try to contacting owner.
It is in the mail, sir.
Yes, madam. It is in mail. I have clicked on that link and showing the error. Try to contacting owner.
Yes, ma'am. Same has happened with me.
Yes. Error येते.
Okay. Now see.
It's working now.
Okay, thank you.
Hello, ma'am.
For students, please wait. I'm sharing the quiz link to you. Oh. Actually, wait.
Okay, ma'am.
Dear students, please let me know. Is it available to you also now? Your link is different. You must have received the link on your mail. Please let me know whether it is working or not. Sakshi, is it visible?
Oh, just a second, ma'am. Checking. Yes, ma'am. Visible.
Okay.